Here we have another projectile motion question. And as before, step one is always draw a labeled diagram. Please don't skip this step. So much chance of making mistakes if you just skip this. Because for example, we have two distances, the height and the horizontal distance. Pretty easy to mix those two up. So let's see, we fire this at an angle of 35 degrees, like so, relative to horizontal, at an initial speed, like so, of 20 meters per second. Great, goes up, comes back down. We want to know the horizontal distance the object travels, sometimes called the range. I'll call that an x dimension factor. The height here would be a y dimension. We also want maximum height. Let's ignore that one for now. Let's do this one. So step one, draw that. Step two, your components, your component chart. The x is the side to side, and the y dimension is the up down. Remember, in your x dimension, this is the only equation you really need, because it's uniform motion in the x. Speeds up in the up down, but uniform motion in the x. Y dimension, any one of your acceleration equations could work. But step three, typically for all these, is to find the time. And I'm going to say, well, it's always this equation, the x dimension. In the y dimension for these up-down questions, it's probably going to be this equation. No guarantees. I suggest you look at it first, the acceleration equation. However, note this velocity here, initial and final, this initial velocity is not 20. No. This 20 is going at an angle. This is talking y dimension only. So I need to, even though it doesn't really ask for it, I need to solve for the components of that 20 meters per second. It's launched at an angle, going upwards like this, 35 degrees. I need to find the y dimension of the velocity and the x dimension. Now the x dimension, whatever I find, it's going to be a constant velocity. Gravity doesn't pull sideways. This one is going to change. How's that going to change? Well, consider. Initially, in the y dimension, it's going straight up like that. At the very end, it's going down like this. And these two will have the same magnitude, opposite direction. Goes up, comes down. At the very top in the y dimension, the velocity will for a slight moment be zero. As far as the x dimension goes, whatever it is, it'll be a constant value. So I need to compute these two. Well, this looks like it's opposite the angle. I know the hypotenuse. So I'm going to say it's the velocity times, well, opposite is going to be sine of the angle. Where over here in the x dimension, it's adjacent to the angle. So it's going to be this hypotenuse velocity times cos. So 20 meters per second times cos of 35. Where over here is 20 meters per second times sine of 35 degrees. Let's calculate those two. Make sure we're in degree mode. Yes, we are. So 35 cos times 20 equals. So the x dimension of the velocity, which will be a constant value, is 16.383 meters per second. Where the y dimension over here, so 35 sine times 20 equals 11.47 meters per second. So step one, label diagram. Step two, the chart. Make sure you do this step always for these type of questions, the up-down projectile motion. Some people call them type 2 projectile motion, and that's fine. And our step three is going to be solve for time. But before we do that, let's take these two numbers and put them over here. So the x dimension over here is 16.383 meters per second. Where the y dimension of this v, 11.472 meters per second. Only this number will be used over here. Only this number will be used here. It's 20 meters per second. It's done its job. Don't use it over here at all. No. It's done its job, okay? Now, as usual, even though it's not asked for, I need to solve for time. Now, can I solve for time over here? Well, let's see. I know the Vx, but I don't know the D. I can't solve for time here. Let's enter the other dimension here. So, do I know the acceleration? Yes. I'll say down is negative, and negative 9.81. Do I know the V's? Yeah, sure I do. So I'll use this equation to solve for time. So T, bit of algebra here, Vf minus Vi over A. Now, careful with the substitution here. The final velocity in the y dimension is actually the same as the initial velocity, but opposite directions. This one will be negative, because I said down is negative. This one will be positive, but not positive 20. No, no, no. The final velocity is going to be negative 11.472. The initial velocity right there is going to be a positive 11.472 meters per second. The acceleration, negative 9.81 meters per second squared. Now, careful, careful. This negative is here because of vector directional considerations. This negative is here simply because of the equation. Your calculator doesn't care. It's going to treat them the same, but it's so important, that negative sign. People are going to forget. Don't put the 20 over here. It's done its job. So, let's see. Run those numbers through my calculator. And I'm going to get a T of 2.3387 seconds. That's what I'm going to get. Great. So that's the time in the air. The time to go up and down, but it's also the time to go sideways. So over here, I can take this time. Time is the only number you can count on to cross this dimension, this wall. It's a beautiful wall, and time will cross it. D equals 16 in the x dimension, 383 meters per second, multiplied by the 2.3387 seconds. The x dimension, the range, therefore is going to be 2.3387 times 16.38. It's going to be equal to 38.3079 meters. So I look back at my numbers. I'm going to go for 2 single digits. And so the distance traveled horizontally on the ground will be 38 meters. Great. Now, as far as the height goes, well, it's still a distance, but it is this distance, a vertical height. So a dy, vertical distance, is a height. That's why I'm asked for maximum height, maximum altitude. So that's a y dimension factor, not x. No longer care about the x. So this is what I'm going to go with here. This is the information I have, negative 9.81. And as far as doing this, there's actually a couple ways to do it. I think I'll use this equation. D equals VIT plus 1/2 AT squared, a very common popular formula on your formula sheet. And I'm going to make the claim that the initial velocity equals 0. How can I make that claim? Initial velocity not 0. I can make that claim because I'm going to say, well, let's say the object starts from here. I know it doesn't, but let's calculate the distance it goes down. If I calculate the distance goes down, the velocity at the very top is 0 in the y dimension. So that'll make this equation reduced to the simpler form. And now that I have that, I can calculate the distance it goes down in the y dimension. 1/2, 9.81. Now the time, now watch what I do with the time. I'm going to take the time, which I had calculated before, and which we got as 2.3387 seconds, but I'm going to divide it by 2. I'm going to divide it by 2. And of course, don't forget to square it. Why divide it by 2? Because half the time is required to go up, and the other half to go down. I'm only calculating the time to go down to get the distance down. very commonly forgotten. Divide that time by 2, just the time to go down. So the distance down in the y dimension is going to be, let's see, 2.387 seconds divided by 2. Don't forget to square it. Times 9.81 equals divided by the 2 because of the 1/2 right there. Is what I'll get. And that gives me a dy. It's going down 6.699 meters. There's a lot of digits there. It's going down. I don't really care about the down. When it came down, yes, but I want to know how high it came down from. So I'm going to say the altitude, the maximum height, in this case, 2 digits, is going to be 6.7 meters. Projectile motion, done.